Yes, all right. So thanks a lot for the introduction. First, I want to say that I'm really humbled to see so many faces here in the room. You've come here just to hear me talk about what I've been doing for the past 3 years. So I'll try and make it understandable for most of you. Well, it's about inferring geometric modeling operations, and we will use graph transformation rules for that. I've worked here at Centrale Supélec under the supervision of Pascal Legal, and I've also had the pleasure to be co-supervised by Agnès Arnoux and Hakim Balaoui at Poitiers. So my thesis, it's about geometric modeling. The question is, how can we make such scenes? Well, the first step is to build a rough shape of the objects. And then we add details. This detail, it can be normals, displacement, noise, and finally, we render the scene to obtain the object. Well, my thesis, it's about the first part, the creation of the objects. And in this scene, there are 3 arches, rock arches, and I've built them starting from an initial phase that I've extruded to obtain a surface, and then I made a hole in it, and finally I removed the bottom part. Well, this is a sequence of modeling operations, and I could have made them in a variety of tools, software. Some of them are open source, like Blender, and others are proprietary, mostly dedicated to specific domain, like Katia for computer-aided design, or Maya for movies. You have an issue, Bedrish? Okay, fine. Then I'll continue. So we will be talking about modeling operations. A modeling operation is simply a transformation of a geometric object into another geometric object. And well, on your computer, it looks like this. So this is the Seagull code written in C++ that describes the modeling operation that you can see on the left. And the usual way is that you write the code, and then you use it in order to modify your objects. Well, the ambition of my thesis is to go in the reverse way. We'll start with a visual description of our modeling operation, and we will try to retrieve the code that generated it. While retrieving the code, it can be difficult. So we will introduce an intermediate description of the modeling operations using a domain-specific language. The idea is that this domain-specific language, it's an abstraction of our modeling operations, and it can be used to generate code. And in my thesis, I used the domain-specific language of Jerboa, and now we can rephrase the question as, given a visual specification of our modeling operation, how can we retrieve the operation written in our domain-specific language? First, I will give you some insights about this language. It's written for the model of generalized maps, and it comes equipped with a syntactic analyzer that gives us, in a sense, feedback, giving us some pointers where maybe we made mistake writing the modeling operations. And it has also already been used for several applications in different domains. And an operation, it looks just like this. The image you see on the top right-hand corner. Maybe at the moment you don't understand it, so I will try and explain it. The idea is to sew 2 faces. So we start from 2 volumes, and in a sense we glue them together. And we model this with a rule. We have this arrow here, and everything that is left of the arrow is the description of the object before the modification, and everything that is right of the arrow is the object after the modification. And because we are sewing 2 faces, actually, the left part, it's only 2 faces. We have 2 nodes. Each one represents 1 face with the constraint that they should be isomorphic. And then on the rule, we can see those loops written 3, meaning that the volume should be 3. And we can see on the right-hand side that the loops have been replaced by an arc, meaning that essentially we've stitched together the 2 faces. So that's, in a sense, a broad description of Jerboa's language. And how does it work? It relies on the theory of graph rewriting, using the fact that we will model the object with graph, and then we will transform this description of the modeling operation into a graph rewriting rule, which will be then used to directly modify the representation of the objects. And before moving to the main part of the presentation, I just want to introduce this example, which is the phase triangulation, and we will use it both for explanation and illustration throughout the talk. So we start from a face, and then we will replace it with triangles. As many triangles as we had initial edges in our original face. And obviously, we need to add a point in the middle, a vertex, that is common to all the faces. So now, the talk. The talk is about inferring modeling operations, and we will start by describing the objects, so the model that is used to represent the objects, so generalized maps. Then I will explain briefly graph transformations in order to give you some insights about Jerboas language. Once we will have this language, we will be able to retrieve the modeling operations in this language, given the visual description. And the last part will be dedicated to some applications of the method I've developed, and I will also present the tool that I've implemented using Jerboa. So first, the description of the objects. As we saw, the objects are modeled with graphs. So a graph is simply a set of elements that we call nodes, and then we add relations on those elements. And those relations are represented by arcs that link together the graph. And because we will want to modify this graph, we need, in a sense, a way to map one graph to another graph. So we need a function, which is actually called a morphism. We need the morphism on graphs. And the idea is simply that a graph morphism should map the nodes of the graph onto the nodes and the arcs onto the arcs. So for instance, the two green nodes are mapped onto the green node from G to H, and the elements in black are elements that are not mapped from anything in G. And obviously, we can add more information on those graphs. So we can add labels, types, and attributes to have a deeper understanding of the object. Now that we know what a graph is, how can we use them to represent objects? So that's an object, and that's the representation as a graph of this object. The structure is called generalized maps, and it encodes both the topology of the object and its geometry. On the topological side, we use the structure of the graph to help us. So in our case, we have arcs that are labeled by dimensions. So 0, 1, and 2, 0 in black, 1 in red, and 2 in blue. And this describes entirely the topology of the object. And then we want to add geometric information. So we will add information on the nodes of the Gmap, which are called darts. So on each dart, for our talk, we will add colors, and a position represented by letters. So now we have topology and a geometry. But I've been lying a bit in a sense that the topology, we still need to retrieve it on the graph. Because if I take the dot D here, it belongs to the vertex that is actually represented by a subgraph. And the subgraph, we call it orbit, and it relies on a subset of dimensions. So for a vertex, we use the dimensions 1 and 2, and then we can add a geometric value, so an embedding, a position, in this case, K for the vertex associated to the dot D. And similarly, we can add color. We will add colors to the faces. So we will retrieve a face with the orbit 0, 1, and then we can add a color. Now we have the complete description of the objects. Now the question is, how do we modify them? How do we formalize modeling operations? And we will use graph transformations. In a sense, graph rewriting, it starts from a left-hand side L to be rewritten in a right-hand side R. And because we do not have enough information when this is graph, we add an interface K, which in a sense translates the preserved elements through the transformation. and it also allows us to reconnect the modified part to the global context of the graph. So now, if I want to modify a graph, let's say a graph G, I will need to find an occurrence of L in G. So for this, I will use simply a morphism from L to G. And then I will remove everything that is in the left-hand side but not in the interface. The construction is called a push-out. Yeah, and then I will do another one to add back everything that is in the right-hand side and was not already in the interface. And this method, it works directly on Gmaps. So here, I have the hexagonal face, and on the right-hand side, I have the triangulated hexagonal face. And now I can look for an hexagonal face in my object, so that I can find one in the middle, and I apply my rewriting, and I obtain a triangulated object. But the issue is that triangulation of a face, semantically, it's just the triangulation of a face. It does not depend on the fact that we triangulated an hexagon. So if I start with a square, I should be able to describe the triangulation of a square in the same manner that I describe the triangulation of an hexagon. And this is, in a sense, where the magic happens and where Jabber comes into play. So we will abstract over this graph rewriting by means of abstracting over the topology using the orbits that I've defined. And just for clarification, we will leave the interface implicit, and every node that has the same name in both the left-hand side and in the right-hand side belongs to the interface. So now, about this triangulation operation. It works on a face, so the orbit 0, 1. And if I look at my face with only one dot, and I take one dot to represent the complete face, I see that one dot has one incident arc in black, and one incident arc in red. And this pattern, it happens everywhere on the face that I want to modify. And now I will, in a sense, reason at the level of one dot instead of reasoning at the level of the face. So I keep my dots, and in the right-hand side, I see that there is, again, a node N0. So I will keep all the dots that are associated with my face. But I also see that the label on the face is different. We relabeled the face from 0, 1 to 0 and the deletion symbol, meaning that the red arc here has been deleted and there's nothing left between A and B. And now for the other nodes, so N1 and N2, we will copy the initial dots and perform relabeling in the same manner. So for the first added node, N1, in yellow, there is a label deletion N2, meaning that we deleted the black arc here from here to there, and the red arc has been replaced by a blue one, so dimension 2. And similarly, for the last node, which represents the dual vertex of the face, label 1, 2, we've simply changed the dimension 0 into 1 and the dimension 1 into 2. And now we have 3 sets of nodes. The one in blue, the one in yellow, and the one in green. But we still need, in a sense, to reconnect them. So that's the point of having arcs between the nodes in our whole scheme here at the top. The first one is labeled 1. So we add an arc between each dot and its counterpart from the blue set of dots to the yellow set of dots. And again, for the last arc, the 0 arc from N1 to N2, we add arcs for all the copies. And this explanation that I did, I never talked about the fact that the face was a square. But this triangulation, it could also work with any topology of a face. So I can take again my hexagon, and it works just the same. Well, this is an intuition of how it works. Well, how does it work in practice? What's the theory behind this? So we have our graph to be modified. We have somewhere a description of the modification, and we want to obtain this. Let's get rid of what it actually represents. We'll call the first one P, the second one pi, and the third one that we want to compute, the instantiation of P and pi, written iota P and pi. Now the first step is that we embed our graph to obtain each possible relabeling. Then we perform a product which was shown by Bauderon at the end of the 1990s to be a way to simulate the application of functions. And now we have our modified graph, which we simply have to move back to our initial category. So in a sense, move back to Gmaps, and we obtain our modified Gmap. Well, this is simply the instantiation of one part of the rule. And the complete construction, well, it looks like this. Maybe you're a bit lost, but let me give you just what is essential on this diagram. The first part is we start from a rule scheme, so a left-hand side, an interface, and a right-hand side. We start from a Gmap, and this category called everything, it yields there a modified Gmap. The second part that we can highlight is this product construction that I've explained in the previous slide. Well, it happens both for L, K, and R. And the last point that I want to highlight is that the last step is simply a DPO rewriting step, so just like the triangulation of the hexagon at the beginning. And this concludes, in a sense, the description of the modification of the topology. But now, what about the geometry? I said it was values added on the nodes of the graph. So I can model them using algebraic data types, such that I have functions that allow me to simply modify the value. So maybe I have a function add that adds a vector to a point, and then I obtain a translation. Maybe I have a function that is called middle that computes the middle of a set of positions. And I can have scale function. I can have everything. I just need to specify it properly. But still, there is something that needs to be taken care of. It's the fact that, in a sense, the geometry, it relies on the topology. Because the geometric information are added to subparts of my graph, I need to ensure that I can access, through the topology, the geometric values to ensure consistency. So I add topological operators. The first kinds are neighbor operators that, given a dart, allows me to access its neighbor dart. So for instance, if I start on the dart A here, if I get its 0 neighbor, H, its 1 neighbor, G, and finally its 0 neighbor, F, and then I can ask for the position. And here, if I compute the same pass, I obtain that the position is C. And similarly, I can ask for the position of a color, but since all the points are yellow, whatever pass I would write, I would still obtain yellow. And the second kind of topological operators are collect operators. They allow me to retrieve all values in a given orbit. For instance, I can retrieve all the positions in the orbit 0, 1, so all the positions in a face. And there, if I quotient my graph by vertices, I will obtain one position for each vertex, so A, B, C, and D. And similarly, if I quotient my face by a face, I obtain only one value, so only one color, so yellow. But the question is that we should not modify graph directly, or Gmap, sorry, directly at the level of Gmaps, but rather at the level of schemes, rule schemes. So we need a way to ensure that whenever I map my rule in somewhere into the graph to be modified, my node, it actually encodes for a bunch of nodes, for a set of nodes. Here, 8 nodes, meaning that the computation that I will write on the node N2, it should be valid whatever node, whatever dart I use to compute, to perform the computation. So if I take back my triangulation operation, I want to add my position as the barycenter of the initial phase. So 1/4 of the sum of A, B, C, and D. Well, summing over the points and taking 1/4 is simply computing the middle of the points. So I can get the middle of the set of points. Now, the set of points, we can retrieve it with our collect operator. And now we have an expression that is computed starting from A, but the middle of the set of position in the face incident to A, it would be the same if I computed it on B, C, D, or whatever dot. So my expression, I can abstract over A, replace it with N0, and now I have both a topologic description and a geometric description that does not depend on the fact that my face was a square. And now I can triangulate properly any face. The question now, this is the last question on this description of my graph transformation rules and my language, is that if we modify a GMAP, we should obtain a GMAP. So if and I also want, because the ambition is to write rules in a software, I want feedback, because if I write something wrong, I want to be able to first say, okay, there's an error, and maybe what kind of error it is. And obviously, we can have topological errors and geometric errors. For the topology, there's a condition that says that any 0202 pass should be a cycle. It ensures that faces are glued together along edges. And if I take this rule, it's the same more or less as the triangulation operation, but I've flipped the dimension in the label. I've replaced 1, 2 by 2, 1. If I perform the instantiation, I obtain this graph. And now if I extract the edge, I will obtain a graph like this, which is not an edge, meaning that there is an issue somewhere. And in our language, we can actually compute the fact that here 2020 or 0202 is not a cycle because it's computed from a face which can have any topology. In a sense, so we can solve this inconsistency at the topological level, but we still have inconsistencies at the geometric level. Here, the condition is that all the dots in a face should have the same color. And if I take this rule, which removes an edge between two faces, just like we can see in the top right-hand corner, and if I apply it, well, I extract an edge, remove some parts, and then reconnect the added parts. And then we get a face, which is green, blue, and the mix of the two colors, so 3 colors in total. I'm breaking the geometric consistency. And I've shown that we can extend this rule to obtain a solution that, regardless of the topology, will ensure that we never break this geometric consistency. So to recap about everything that I did in the formalization of this language, first I proposed formalization of previous works done by Thomas Bellet and Mathieu Poudret during their thesis, using graph products and using rule completion for the geometry. And I've also shown that if we reason at a local scale rather than directly at the level of the orbit, we can weaken the conditions and obtain necessary and sufficient conditions instead of only sufficient conditions, which will be, in a sense, helpful when inferring modeling operations, because we'll know that whatever we inferred, it's valid. And finally, this framework, this extended framework, also allows to model modifications of oriented maps, which is formalization of half edges and generalization of half edges, which is, in a sense, the most popular model in topology-based geometric modeling. So we can model, using graph transformation, formalize the modeling operations on those oriented maps. And a quick disclaimer, if you read my thesis, the rules looks like this, which is not exactly what I will show in the talk. In the talk, it's job was language, and this is essentially the extension. And I mean, you can see that it's more or less the same, but in a sense, it also allows directly in this framework to write this. This is, again, the triangulation operation, but on oriented maps. And there are some stuff like this A, which with a conjugation symbol over it, that we cannot write directly in Jerbois. So I've, in a sense, extended Jerbois to work with oriented maps. So now the second part, the inference part. The question is, we have this modeling language. We can use it to perform modeling operation. How can we retrieve the modeling language? And in a sense, it's as simple as reversing the arrows. It's as simple because it's simply reversing the instantiation process. And globally, this inference mechanism, it lies in a more general workflow in which we start from two instances, so the object before the modification, the object after the modification, in which we add some more information on the preserved elements through the modification. And then this is the topic of this part. This is how can we retrieve the modeling operation in Jerbois. So I'll start with the topology. I'll take again the triangulation of a face. So we have our initial face here in green. We have our target after the transformation phase, so the triangulated face in blue. And I add information. Which are the preserved elements? And I model this with arcs on the graph. So these are the kappa arcs that goes from the green to the blue. And now there, I actually have all the needed information to retrieve the modeling operation. And in a sense, I will fold this representation just like I unfolded it when I performed the product. So I will start with a dot, and I will also ask as input the parameterization of my modeling operation, so the orbit tab that should be used to fold my rule. And then it's simply a graph traversal algorithm. So I will simply go through my graph and fold it either an arc or a node, such that I can retrieve my modeling language in Jerbois language. The first step is actually to simulate the first step of the instantiation. I will compute all the dots that belong to the orbit pointed out, given as input. So in my case, my face. I have now these 8 dots that will be used as reference through the folding. So then on the scheme part, I know that the first node should be labeled 0, 2, because it was the input. Now, on the set of dimensions that I could have 0, 1, 2, or kappa. Kappa is the preservation arcs. So I've already added 0 and 1, and I can then try to extend either 2 or kappa. There is no 2 arcs in my faces because they were extracted. So I only have my kappa arcs. And I will try to traverse simultaneously all the kappa arcs from my initial face. And they actually exist. So I will assume that it is possible, and I add a node here. And I will say that, okay, folding the kappa arcs is valid. I can add the kappa arc to my rule scheme. Now the question is, what's supposed to be the label of this node? So I can look at the arcs between the dots that are counterparts of the initial dots associated with N1. So I have these 8 new dots. And I can see that whenever there was a black arc, there is again a black arc. But whenever there was a red arc, there is nothing. So I will assume that the relabeling should be 0 and the deletion symbol. And then I verify that this is valid everywhere. And it's the case. So I've correctly folded the node. Then I can iterate. I will now need to fold an arc, and then a node, and then an arc, until it reaches the end. There's 2 ways you can stop. First, we get into a failure state where we cannot fold properly either the arc or the node. And the second one is we've seen the complete graph, and then it's done. We have a rule. I mean, I'm lying a bit because that's not the rule. I'm missing the arrow here somewhere between the left-hand side and the right-hand side. But I know that some darts, they belong to the initial instance and the other to the after instance. So I can split this graph and then add the arrow. It's a bit more complex because this kappa arcs in pink before, it stated the preservation of some darts. So I need, in order to perform the computation of the interface properly, to add, to rename, this node from N1 to N0. But now I have completely folded my graph and I have complete description of the topology, which leads to some question. First of all, is it correct? Well, I've shown that it is correct. I've shown that if there is a way to fold the graph, then the algorithm will output the properly folded transformation. And if there's not, the algorithm will stop in one of the failure state possible. But there's still some question. If I take this rule, this before instance and this after instance, and I try to fold it on the surface orbit, so 0, 1, 2, it will not work because I've only modified one face out of the complete surface. So it cannot be folded using the 0, 1, 2 orbit. And probably what the user wanted was to specify the triangulation of a surface, so an object just like this. And now the algorithm will work, and I will obtain this rule. And now the question is, we have this before instance, we have this after instance, we retrieve this transformation, but we still do not have any geometry. Well, Jabwa will tell us actually that this node, it's missing some information. It's missing some geometric information. So I know that, okay, this node, which corresponds to the dual vertex, maybe it needs a position value. So now the question is, which one? We will make some hypotheses. The first one is a linearity hypothesis. We'll assume that the target position is computed as a weighted barycenter of the initial positions. And so we know the initial and target position, and what we want to retrieve are the weights. And we will add a degree of freedom by adding a translation factor, T. So that's, in a sense, the framework in which we will try to retrieve the geometric expression. But the geometric expression, it does not directly modify GMAP. It's expressed at the level of the rule scheme, which performs an abstraction of the topology. So I need a rule, an expression that is, in a sense, topology independent, because I need something that is computed properly regardless of the permutation on the darts. Well, we already have the answer. We know that we can collect values, and this collection operators, they do not depend on the topology. So the methodology that I propose is to use points of interest computed regardless of the topology. I will explain them on this 3D object just for the sake of exhaustivity. So given a dart D, I will replace it by the position of all its topological cells, so the barycenter of all its incident topological cells. So for D, I get the position of its vertex, the midpoint of its edge, the barycenter of its face, the barycenter of its volume, and finally, the barycenter of its connected component. And now I can rewrite my system using these points of interest. So coming back to our triangulation operation, we want an expression for N2, and we will assume that it can be written as a linear combination on the points of interest computed from N0. So now, because each dart should yield the same correct result, we will have actually 8 equations generated from this global equation. Then we split it on the axis. So one for X, Y, and Z. So we obtain 24 equations. And because the weights should be the same for the globe, in the global equation should be the same for all the equations, we actually obtain a system that is made of 24 equations and only 8 variables, one for each of the points of interest, and 3 for the translation factor, translation on X, Y, and Z. And then, how do we solve it? Well, we give it to a CSP solver, which can be, in a sense, seen as a black box, to which we feed an equation, and which will give us a solution. I've experimented with the CSP solver from Google, which is called Ortool, and the one from Microsoft, which is called Z3. So now we have our global equation, which we translate into a system, which we feed to our solver, and it gives us a solution. And here we can see that for the triangulation, all the components are null except for the weight of the face, meaning that we've correctly placed the new vertex at the barycenter of the original face. So now let's move on to the fun part, the applications. So the tool that I've made is called Jerboa Studio, in which you can specify the before object and the after object. Then you add some information about the preserved elements, and then you click this button, and it will simply generate you the rules. And you get something like this, where you have here it's the topology, here it's the generated code for the geometry, and actually, because I did not specify the orbit that I wanted to fold the rule, we folded it on all possible orbits, and after some simplification, we obtained 14 different rule schemes that depends on the generosity, in a sense, of the rule. Another example, which is taken from geology, is that we have two initial surfaces in between which we want to fill the void by adding cuboids. These two surfaces should be isomorphic such that we can map each face in the top to a face in the bottom. I use my algorithm, and I obtain this rule. And because there's no topology at this point, because I did not add any position, it's actually really fast, 3 milliseconds. It's simply traversing the graph. And now we have a rule that we can apply to a more complex object. So maybe these two surfaces, and if we apply this inferred operation, we obtain all these cuboids that have properly filled the void between the top and the bottom surface. Now let's complexify this example. We'll add many layers between the top one and the bottom one. And because a color is the same as a position, it's simply a vector, we will also add colors and try to retrieve the colors. While we run the algorithm, and we obtain a rule like this. Maybe it's hard to read, but it doesn't matter because we have the rule, we will be able to apply it. I just want to stress that the inference of the geometry takes slightly more time than the inference of the topology because solving the system can be quite difficult. So now, applying this operation, we take back our two initial surfaces, and then we apply it, and we obtain completely subdivided surfaces. We can see that even though we inferred as shades of gray between black and white, we've been able to properly interpolate the colors between green and orange, and also we have properly interpolated the heights of the different layers and the positions that tends to follow the original deformations of the surfaces. And other types of examples that we studied are subdivision schemes that can be applied recursively on an object to obtain more details. Here's the do-Sabin subdivision. This is an object. This is the application of the first iteration. We can use them to infer a rule here. Then we apply it again to obtain the second and the third iterations. And now these are simply objects. So I can use my first and my third object and infer a rule that performs the second iteration. And similarly, a rule that directly performs the third iteration. And believe me, you do not want to write this. Another funny example that I want to highlight is this Menger 222 operation. I found it in a paper by Ricom and co-authors, where they wanted to study whether this object could be unfolded as a sheet of paper, completely planar sheet of paper. And well, there was no way, there had no description of a transformation from this object to this object. So they built it by hand. Well, I did the same, but now I have my mechanism. So I can infer the transformation, and I can apply it again, and I can obtain a more divided object that they couldn't do. And this operation, I can also use it on different volumes. So, I mean, that's a lot of things that they couldn't do directly in their paper. And there's still some limitations about this geometric inference. Here it's the von Core snowflake operation, which takes a square and builds this snowflake-like object. If I infer it, the first iteration is valid. I will correctly retrieve the transformation, but if I iterate this object, well, it tends, the subsequent iterations tends to diverge from the object that we would generate normally. And in a sense, it's simply because this object is out of the scope of the hypothesis that we made at the beginning, so it's not a linear combination of the original positions. To conclude on Jerboa Studio, it's within the ecosystem of Jerboa, in which there is a tool that allows you to write rules, tools that allow you to view the objects and modify them, and it relies on a rule application engine. And, well, the thing that I had to do is to tailor this viewer to obtain two of them, and then I added this inference module, which take information from the viewer and outputs a rule in the editor. And I mean, because Java is a wonderful language, Java is also a wonderful language, but I was just talking about Java. Okay, Java is a wonderful language. We can do reflection and directly modify the states of the code to add the inferred operation back in our viewers. So now it's time to conclude. I still want to give some information about related works and future works. When I started studying this question of inferring modeling operations, I quickly found that actually there was not a lot of works on this topic. Most of the works, they were trying to find solutions to generate an object given some a priori objects that we wanted to imitate in a sense. That's the case in inverse procedural modeling, where we try to retrieve parameters on rules. On L system, we can also extend this inference to retrieving formal rules. And in CSG, the idea is to build a tree that generates an object given a shape. When I studied my algorithm to perform subdivision schemes, I found this paper, which was published 2 years ago, which is in a sense the jewel of my work, because it assumes a completely set topology where everything is triangulation. And the only possibility to modify the topology is through the loop scheme, which builds triangles out of triangle. And the interesting part of their work was to obtain the correct weights given different inputs. And I believe that inference has also been studied in the fields of graph transformations, but it's mostly domain dependent. And in a sense, my work is also domain dependent. And to sum up, I've explained a way to retrieve modeling operations out of a visual description. On the topological side, it's a folding algorithm. On the geometric side, it's a CSP with values of interest, and everything is implemented in Jerboa Studio. And I want to stress out that everything here is actually only possible because of the formal part of graph transformation, in the sense that this graph transformation method gave us some guidelines for the inference, and I also try to improve the formalization of Jerboa's language using graph transformation. As for future works, first, there is this step, which is mapping the before instance onto the after instance. I've talked to some people about it. They all told me, well, this is really trivial. Then I gave them a sheet of paper, a pencil, and after 10 minutes to an hour, they said, okay, I cannot do it. So, I mean, there's probably a solution, but there's a lot of difficulties that we should map properly both the geometry and the topology. Here it's probably simple, but if I gave you a really complex object, there might be several ways to perform this mapping. The second one is that, well, we made some hypotheses on the geometry. So if we extended it, maybe we could retrieve more complex operations. This is the Catmull-Clark subdivision, which is topologically equivalent to the quad subdivision. But here we have an expression that is out of the scope of what we did, so out of our hypothesis. So modifying our hypothesis would maybe allow us to retrieve this operation. And finally, we borrowed a lot of knowledge from graph transformation. And maybe it's the time to give back to the graph transformation community. And it would be really nice if I could translate this algorithm that I've developed into categorical notations and construction that are used normally in graph transformation, in the graph transformation community. And I believe this is the end of my talk.